production. And these are kind of standard stories, but I will add a non-standard thing, which will be a non-standard cosmology. So the production basically of axions, of relic axions, cold and hot, during these non-standard cosmologies. So my overview, first I will make you an introduction about why dark matter is a problem nowadays in physics, and discuss about general properties of dark matter, and then convince you that axions are really good candidates for that. Of course, in that motivation, I will center mostly in cold dark matter, but axions actually can produce relic populations in several mass ranges, and also can be hot dark matter. And then I will tell you about the non-thermal production well, first non-thermal production in standard cosmologies, and then I will introduce you my way of parameterizing these non-standard cosmologies. Then I will move, if the time allows, to this thermal production. And finally, I will conclude. This work, these two papers have been written in collaboration with these people here, basically some students of mine, I mean, former students actually now, and Nicolas Bernal from Abu Dhabi and Leszek Roszkowski from AstroCent. Okay, so the dark matter problem. Of course, I'm quite sure you all have your favorite reasons why we should have what we call dark matter, and then choose your favorite model for that. But of course, for centuries, humankind has been speculating about the existence of something that we cannot see. From the Aristotelian perception of the world, this has found sound resistance, and it has to be more than just the picture that we see. And for instance, Galileo Galilei, using a telescope, learned that the faint glow of the Milky Way is actually produced by a myriad of individual stars. And he also found that at least 4 satellites that are orbiting Jupiter, among other things that no one has had observed before. So the lesson there is that the universe may contain more than we perceive by ordinary means, and that the technology is crucial to reveal new forms of matter. The concept of dark matter is certainly really old, but probably at the beginning of previous century, it was more into non-luminous matter. So for instance, in 1933, this Zwickie's famous article that suggests that the coma cluster requires more matter to explain the dynamics of the cluster. And he coined the term dark matter, but more in thinking into faint stars that could not be seen. But with time, we learned that, for instance, hot intercluster gas option to explain the dynamics of the coma cluster was ruled out, and so on. And things got more dramatic when Vera Rubin and Henry Ford started their pioneering work on the velocity curve of galaxies. And well, this led to Vera Rubin to state that there is something fundamentally missing in the understanding of our universe. And like that, evidence piles up, pointing out that we need more matter in the universe to account for the observations. And Sorry, yeah. Also, some evidence appears through gravitational lensing that, of course, baryonic or normal matter can produce this effect. But in order to explain the amount of gravitational lens observed, it is needed much more matter than the visible one. So we cannot explain things like this, like this picture here that we see, only with visible matter. This is another example of lensing. And finally, what is for me the mother of evidences is CMB signatures. We know that the CMB provides this picture of the universe when the universe was 380,000 years old. And the signatures, or in this case, this temperature map of the CMB is crucial to understand that we need more matter than just the baryonic matter observed. So the CMB is not perfectly uniform, has tiny temperature variations, and these fluctuations are crucial clues to understand the distribution of matter in the early universe. So, for instance, the picture we have from lambda CDM is that dark matter was present, and of course, small perturbations in density that have a primordial origin could be amplified to form these gravitational potential wells that over time and under the influence of gravity, these perturbations grow and they attract matter, and this at the end leads to the formation of structures. So in here you have like the regular picture that we think is what formed the structures in our universe, that the dark matter, well, all fields, of course, have these small perturbations, but since dark matter is collisionless, it can start much earlier than normal matter to produce these potential wells, where then normal matter can accrete and start to gather and to form structures. In a rough picture, if you have these potential wells, photons that are falling in the potential well and that are climbing out of the potential well gain and lose energy respectively, and this causes then differences in temperature in these photons that at the end will provide the CMB. So a detailed general relativistic calculation shows that you can link these temperature fluctuations to density or gravitational fluctuations. And in order to account for this number that is inferred from the properties of the CMB, we know that it cannot be accounted just from baryonic matter, because baryonic matter is only free from photons to form these potential wells at the epoch of recombination. And this time is not enough for these fluctuations because, well, the redshifts is only something around 1,000. And therefore, the production of these gravitational potentials should have happened earlier than that. So at least at matter radiation equality. And And this is why this is one of the greatest evidence of the necessity to account for dark matter in our cosmological model. So some of the dark matter features, in order not to interfere with the large-scale structure formation, the velocity dispersion of the dark matter should be small. That's why we always say that dark matter should be cold. So referring to the kinetic energy of the particles. So should be stable on cosmological scales. This roughly then says that the lifetime of dark matter should be bigger than the age of the universe. If it's at all coupled besides gravity, this coupling should be really, really weak to our visible universe. Should have been present at least at the epoch of matter radiation equality, as I just mentioned. And as far as we know, it's not made of any known matter, like baryons or even neutrinos, because neutrinos do not satisfy this, that the velocity dispersion should be small. And well, these are more or less the known features of dark matter. Now, what if dark matter is made of very light particles? For sure, the most popular picture probably that people have about dark matter is that it's made from really heavy particles that cannot be seen because they are quite heavy and it's hard to produce them in accelerators and so on. So it's hard maybe to picture that dark matter could be made of light particles, and this is what I want to now tell you about. And this is the case of axion-like particles and other relatives of that family that are produced by non-thermal mechanisms such that they can require or fulfill the requirement of their velocity dispersion being small. And this is what I'm going to tell you, so the so-called strong CP problem. So we know the QCD theory describes the strong interactions, and the theory allows for a CP violating term in the action that has this form. So this is the gluon field strength, this is the dual, and theta is just a parameter that should be fixed by the experiment. So this term is allowed because basically there's nothing to forbid that forbids that this term is present in the QCD Lagrangian. And this term violates CP, but strong interactions are observed to be CP conserving. Even though this term is a total derivative, it cannot be discarded because it actually reveals this non-trivial structure from the QCD vacuum. So this term has to be present. One consequence of having or allowing a term like this in the Lagrangian is that you would have a non-zero electric dipole moment for the neutron. The expected value from the quantum field theory calculation would be something around this number, 10 to the minus 14 electron times centimeters. But the measured value is something around 10 to the minus 25 electron times centimeters. And of course, this is just a bound because it has not been observed. So we expect that as the technology and experiments get better, this number will continue to decrease. So this would suggest that this theta parameter or this theta number is actually 0. But we cannot go for this for this choice, because we also have that from the quark mass sector, a similar term arises when you want to diagonalize these complex masses for quarks that are actually also CP violating. So once you make your chiral transformations to remove, let's say, these complex masses, you also end up with a contribution now from this quark mass sector to this theta term, that now in here I put the subscript Q just to distinguish it from the other contribution. And therefore what you need to explain why we don't see this electric dipole moment of the neutron is that the sum of these two quantities that now I collected in theta bar should cancel exactly. And this poses a fine-tuning problem because doesn't seem natural that two quantities that come from really different sectors should exactly cancel. And this is where the axion appears. In 1977, Helen Quinn and Roberto Peccei proposed the introduction, of a new global U1 symmetry that gets spontaneously broken, leading to pseudo-Nambu-Goldstone boson that is the axion. By the Peccei-Quinn mechanism, the axion acquires a direct coupling to the gluon field strength. And the axion has this residual shift symmetry that can cancel this theta bar term, leaving the QCD Lagrangian CP conserving, but to the price, of course, to introduce a new particle. Axions actually end up being pseudo Nambu-Goldstone bosons, because actually the symmetry is explicitly also broken by instantonic effects. And therefore the axion acquires a small mass that is inversely proportional to this parameter Fa, which is the scale at which this new Peccei-Quinn symmetry spontaneously breaks. And since this scale has to be quite big, much bigger than the weak scale, then the axion is naturally light. So for instance, for a scale of 10 to the 9 GeV, the axion has a mass in the MeV range. Besides the coupling to gluons, the axions develop coupling to photons through pion mixing. So basically, they inherit this triangle diagram to two photons. And but this coupling, has to be said, is model dependent. So what you see in here, basically this part here is model dependent. And also, of course, since also is suppressed by this Fa scale, is quite a weak coupling to photons, but this coupling is one of the most exploited ones to search for axions. So the mechanism that solves this strong CP problem, so that makes the axion appear, also is the one who can produce it as a dark matter candidate. So it's actually quite natural mechanism to produce a cold particle in the early universe. So I hope I can explain you well how this works. So imagine we are at a really high energy, really high temperatures, for instance, around this Fa scale, where the Peccei-Quinn symmetry breaks. So the axion is sitting in this in the bottom of this Mexican hat, and therefore has this shift symmetry that allows him to be anywhere around this circle. But once we reach around the QCD phase transition, where the instanton effects break explicitly the Peccei-Quinn symmetry, this changes actually the axion potential, making it tilt. And therefore, the axion loses this shift symmetry, going to the true vacuum. And in the process of reaching this new or this true vacuum, the axion oscillates around the minimum of the potential. And these oscillations are the ones who produce the axion particles, which have a really low momentum. And I will tell you why is that in a moment. And therefore, this produces immediately the axions around this epoch, around the QCD phase transition time. So basically, this is what is known as the misalignment mechanism, because basically the axion potential misaligns at some moment, and it can produce particles from this mechanism. This is how it works for axions from the QCD, what is known as the QCD axion. But of course, if you have a pseudoscalar that can have similar properties in the sense of having a symmetry that gets eventually explicitly broken such that the potential misaligns, this mechanism can be quite generic and not only exclusive to axions. So when this happens, this is the, let's say, the mathematical now form of seeing this production of axions in the early universe. So if you write the equation of motion for axions, assuming, for simplicity, assuming the axion is spatially homogeneous, although you don't need to consider that to show that this happens, but just to have it simpler. In a Friedmann-Robertson-Walker universe, you will find this equation of motion, where A is the axion field, H is the Hubble parameter that depends on temperature, and the axion mass, which also depends on temperature. And you can see that this equation basically has two regimes. At very high temperatures, the axion is actually massless, so this term is not present. And you see that the axion is frozen because of the Hubble friction. So the expansion of the universe doesn't allow the axion to have a dynamic. So it's basically frozen into some constant value. And this is what you see here in this plot for really high temperatures. But eventually, as the temperature of the universe decreases, the axion mass will become comparable to the Hubble parameter. And eventually, this, let's say this damped harmonic oscillator will start to oscillate. And this is, you see what happens here where basically the axion mass, which is this curve here, the green one, in function of over the temperature, and 3h, 3 times the Hubble parameter, when the two more or less cross, the axion starts to oscillate. And these oscillations, I told you, are the ones who produce the particles. In here, I'm considering homogeneous action. So this is what is called the zero momentum or the zero mode action. So this is why you see that actually the action is produced completely cold. Well, of course, it's not only the zero mode that is produced, but just to stress you that this is a really non-thermal production in the sense that the action, the dominant mode of the action is this zero momentum mode.
Paola?
Yes.
Hi. Can I ask you something? I'm a little confused with this mass. You say here that it depends on the temperature, but some slides previous slide you showed the QCD mass that was independent on this parameter. Why here it depends on the temperature, and in the QCD case it doesn't?
Yeah. Well, actually, the mass of the action depends. What I showed is, let's say, the mass at zero temperature, basically. But in the early universe, the axion mass depends on this topological susceptibility of QCD, because it's actually the one who breaks, or let's say changes the potential. So, so the axion mass appears, let's say, not instantaneously, but through some function of the temperature. I will show this function, I think, in like one or two more slides. But yeah, for the QCD action, the mass depends on the temperature. This could not be the case for an action-like particle, for instance, because you don't need to solve the QCD problem. But in order to solve the QCD problem, you need that the action has a temperature-dependent mass.
Paola?
Yeah.
This is Claudio. In the equation there of the action, the A is the action field. This is the same as the theta A that appears in the graph, right?
Yeah, basically this one is divided by the scale, but yeah, basically yes.
Yeah, because I was just wondering a bit, you have the second derivative of A, and then you have MA. So this is not the mass square that appears in the question?
Yes, I'm sorry. It is a typo. You are right.
Okay.
It's mass squared. Yes. Yes. Thank you for noticing. Okay, so so at the end, if you can also solve these equations through WKB method, and you can find analytically the form of the action. Sorry. Oops, this is such a, yeah. You can find analytically the expression for the action field once it started to oscillate, and it has this form here. And you can see that the action field then goes as the scale factor to the minus 3.5. So the action energy density that goes as the action field squared will actually redshift as matter, as we would expect. And therefore it's a uniform oscillating field. And this means that it forms a really coherent state of many particles that are non-relativistic, and this is our cold dark matter population. Well, in here I show you the diagram that allows axions to couple to two photons, and how in this case, Maxwell equations are changed by this coupling. Yeah. This is the status of axion searches exploiting this coupling to two photons. So in here, in the vertical axis, I have the coupling of axion to two photons versus the axion mass. And in here, firstly, as you maybe recall, the axion mass is related to this parameter Fa, which was the scale at which the Peccei-Quinn symmetry breaks. And the coupling to two photons is also inversely proportional to Fa. This means that you can find a relationship between G and M for the QCD axion. And this is what the yellow band is. So the yellow band is where the QCD axion, let's say the parameter of the QCD axion. And everything outside this band, we would say is an axion-like particle, because it might have the same coupling to two photons as axions, but it doesn't solve the strong CP problem. And everything that is colored in this plot is excluded either by laboratory experiments, which are the red regions or reddish regions, astrophysics, which is the green regions, and cosmological, let's say, observations, which would be the blue ones. So as you can see, only a selected group of experiments, and are all laboratory experiments, have been able to touch the axion band in the parameter region where is expected to be cold dark matter. I still haven't told you which is this mass, so I'm spoiling actually that the preferred region where the axion can explain the cold dark matter paradigm is around this micro electron volt. So more or less where this ADMX experiment has been able to touch.
But sorry, Paula, I got confused once again because here have this KSBZ and the other one actions that solves this QCD problem, and you started saying that these ideas are based on a new field, this new pseudo-scalar couples to the gluon, the field strength of the QCD, the gluons. But here you are presenting a coupling between the axion and the photons. This has nothing to do with the coupling of the axion with the gluon. So I don't understand how you can relate these axions that comes from the QCD sector, but now they appear in this plot related to some couplings with the photons.
Yeah, I mean, maybe it's because the story is quite long. So what I did, well, maybe in here I can, so once you work out everything, you will realize that the axion mixes with the neutral pion. So maybe you recall this diagram, if you replace here A by the neutral pion, pi 0. So the axion inherits from the pions this coupling. But I did say that this coupling is model dependent. Let me see where I have it. Yeah, in here. So this is the coupling to photons. And I mentioned that this part here this E divided by N depends on the model, basically. But you always have a contribution that it is in fact model independent. But the strength of this coupling, at the end, it will be model dependent because of this term here. But you expect that the QCD axion, couples to photons in any model, and this is why the band is not actually a line and it's a band, because the line that says DFS set is one of the models that accounts for the introduction of this new Pechet-Quinn symmetry and so on. And KSB set is another model. And in between in here, there are other models. And this give you this E divided by N term that appears in the coupling. So you expect naturally that the axion will couple to two photons, but the strength of the coupling is model dependent.
Okay.
Yeah.
Okay, thank you.
This is the same plot, but now all these pink regions that appeared here are forecasts for new experiments that either are already under construction or are only as prospects. But basically, we expect that the axion, let's say that the field, the field of axions will have news about what happens with the QCD axion in the next 10 to 15 years, where all these experiments can actually be performed. And they indeed will explore the QCD axion. Okay, so now I will tell you about studying this production of non-thermal axions in a different cosmological frame than the one lambda CDM suggests. So our most accepted picture is that the evolution of the universe underwent some cosmological inflationary era, and that the energy scale could have been as high as 10 to the 16 GeV. On the other hand, we only have a test from the early universe from Big Bang nucleosynthesis on, which happened at an energy scale of the mega electron volt. So these two events, cosmic inflation and BBN, are only apart by around 1 second. But the variation in energy scale between these two eras of magnitude. So what could have happened in between, and whether the universe was actually radiation dominated as lambda CDM assumes, is something that is definitely not certain, and could have happened that during this between these two regimes, we could have the appearance of one or more fields that could have dominated the energy content of the universe. Even there is the possibility that reheating itself happened at a much lower energy or temperature than this one here. For that reason, we wanted to explore the axion production in the early universe, considering the effects of this non-standard cosmology before Big Bang nucleosynthesis. So I will repeat a bit only about the misalignment production. So I told you that initially the axion field is frozen at some initial amplitude, but then the instantons change the axion potential, and the axion acquire a mass, and this mass is temperature dependent, as I said, and depends on this topological susceptibility of QCD. So actually this function or the mass, let's say, in terms of temperature, it looks something like this. So at very high temperatures, the mass is suppressed. And as the temperature lowers down, the axion mass reaches this constant value that is the one I showed before that Bastian asked me about. I also showed you, and now in here the typo is corrected, about this equation that gives the dynamics of the axion in the early universe. I also told you that the oscillations start when this 3h is of the order of the axion mass at some temperature, which we call oscillation temperature. So in this plot here, you can see the Hubble parameter and the axion mass. And more or less, when they two intersect, this is what we call the oscillation temperature. Depending on the axion mass, you will have that this crossing happens at a different temperature. And therefore, this is a plot of this oscillation temperature as a function of the axion mass. In here is, just as a reference, the value of 3 times the Hubble constant, Hubble parameter, sorry, evaluated at the QCD temperature. For this work, we worked under analytical results. So we solved the equation analytically, and we also solved numerically, and we found this really good agreement between the two. So of course, the analytical result allow us to explore a bit better, to have a better understanding of what is happening with the axion production in this non-standard cosmology. When you compute the relic density for axions, you will find that you have one expression if the axion mass is below this scale, this 3h at the QCD temperature, or this one here if the axion mass is higher than this scale. And therefore, the axion relic density depends on 2 parameters, the axion mass and the initial value of the axion, when it's frozen at the beginning. So we have only these 2 free parameters to account for the relic density. And of course, you don't want to come back to a fine-tuning problem, because we said that we don't we introduced the axion in the first place to solve this fine-tuning of this theta parameter, that it shouldn't be naturally so small. So in the same sense, we don't want to adjust the relic density just by lowering this number as much as we want, the value of the field when it's frozen initially. Therefore, we took as a natural range to think that this theta value, even though it can have any value between minus pi and pi, we fixed this to be an order 1 parameter. So we selected a window for theta that goes between 0.5 and this pi divided by the square root of 3, which actually looks like a really weird number to choose. But the reason to choose that number, and I haven't told you that part of the story, is that this theta, I mean, this theta initial value, meaning the value of the axion field initially in the universe, depends whether the axion was present during inflation or not. So if the axion was present during inflation, and it had this initial value, and inflation happened, this value got inflated, and therefore it got homogenized in the universe, and it can take any value between minus pi and pi. But if the axion appeared after inflation, this initial value could take different values in different places in the universe, like patches. And therefore you have to average over all those possibilities. And it happens that when you average over those possibilities, you find this number here, this pi divided by square root of 3. So to sum up, if the axion is present during inflation, this theta can take any value. And if it wasn't present during inflation, then this theta is taken as the average over different patches in the universe, and this is that average here. That's why we took this window as a, let's say, a natural window for this initial value of the field. And this leads you to the preferred axion called dark matter window, because you see here we have in this plot this initial amplitude. Sorry, again. This initial amplitude versus the mass. And if we concentrate in this window that I'm telling you about, you find that the axion can explain the cold dark matter paradigm between these numbers here, 10 to the minus 6 electron volt, and a bit more than 10 to the minus 4 electron volt. So this is your preferred parameter space where to search for the axion as a cold dark matter candidate. Now I will tell you some features about non-standard cosmologies. We will consider the existence of a particle field phi that will have a general equation of state omega in here, that during certain period dominated the expansion of the universe before Big Bang nucleosynthesis. And we assume that also before Big Bang nucleosynthesis, the field decayed into standard model radiation, meaning decayed into the thermal bath with some total decay rate gamma phi. So this is how it looks, the energy density plot for this new field and the radiation energy density. So the continuous black curve is the radiation energy density, and the red one, the dashed red one, is the one for this new field. And we start in this stage 1, or yeah, let's call it stage 1, where actually radiation dominates over this new energy up to a certain scale, which we call equality scale, just EQ, where actually the two become equal. And then this new field starts to dominate. And then we are in this stage 2, where the new field dominates over radiation and it doesn't decay. So you see that basically the energy density of radiation is unchanged by the presence of this new field. But then we arrive to the stage 3, where this new field starts to decay and therefore injects entropy into the thermal bath. And then the energy of radiation increases. And then once the field totally decays and stops to dominate over radiation, then radiation just keeps its normal evolution. So for instance, this plot here is made for an equation of state for matter, omega equals 0. We chose this equality temperature, 1 GeV, and the decay temperature, what we call T end, which happens in this redshift here, sorry, this scale factor R end. We took equal to around Big Bang nucleosynthesis time, so 4 mega electron volts. So this is the way we implemented the non-standard cosmology. So this is here is the equation for this new field. And this is the equation for the radiation, or let's say the thermal bath. And here you have the contribution or the decay, let's say, to the thermal bath. And therefore, the Hubble parameter now is given by, besides the contribution of radiation and the axion that is actually negligible, the contribution from this new field.
Paola, considering this scenario, can we say something about the mass of this phi particle, or whether this particle must be in thermal equilibrium with the rest of the standard model? Is that possible to infer from this behavior?
Well, about the mass, it's encoded in here in this parameter gamma, and yeah, I mean, of course, is coupled to the thermal bath, in the sense that the energy transfer goes to anything that is in thermal equilibrium in the primordial plasma, let's say. And this means that if axions are actually not in thermal equilibrium, because they are produced out of equilibrium, they will not receive this entropy injection.
So this phi particle, so for instance, it's as simple to say like the mass of this phi particle is above 1 GeV, or you cannot infer that, for instance, because it must behave as matter, right? W in the equation of a state is equal to 0, but necessarily its mass must be above 1 GeV.
I mean, no, I'm not saying anything about its mass in here. I mean, this is the equality temperature. So basically, the moment when the energy density of this new field is equal to the energy density in radiation. Of course, here I took as an example an equation of state for matter, but actually we also checked other equation of states. So so you don't in principle need that it behaves like matter. So it could be something like an inflaton, let's say, if you are thinking in low temperature reheating. And in this scenario, this stage 1 would not be present. But it is it's not necessarily that is something that behaves like matter.
But just, I mean, in the epoch 2, number 2, if my particle, the phi particle, has a mass of 1 TeV, I would expect that its Boltzmann suppressed and it behaves as a matter. But
yeah,
if
sure.
its
Yeah,
mass is, let's say, 5 MeV, I would expect that in the zone 2, it behaves as radiation.
Yeah, yeah, I understand now. Yeah, of course, in that sense, I mean, you can construct the potential of this field because you remember that actually the equation of state is related to the potential. So once you construct your potential, you will find the equation of state that it has and whether it behaves as I'm showing here. In that sense, we are agnostic about what this field is. I'm not referring to any particular model. And I think Diego has also a question.
Yes, Paula. So given the way in which you are writing the Hubble parameter, the Hubble expansion rate there, I would say that rho phi is behaving as radiation. Otherwise, in that sum, what you have is the contribution of rho A and rho R, but not rho phi, because rho phi will be subdominant if it's matter, right?
Yes.
Sorry, Diego, I'm not sure if I follow. Can you please repeat?
Yeah, so you have 3 terms in the expansion rate. For them to be of the same order, they should be of radiation type. Otherwise, the one which is related with phi will be subdominant, right? So that means that in there you have 3 contributions. In reality, what you call radiation is the contribution of phi, R, and A. So electromagnetic radiation plus neutrinos plus rho phi plus rho A, right?
Yes, let's say in here I'm putting all the standard model.
Exactly. Yeah.
Yes.
So at the end, you do change the radiation density, because radiation is everything which is relativistic at that era, right?
Yes. Yeah, so in that sense, to parameterize this energy density, we use the degrees of freedom and how they change with temperature. So this is why you see in here some small changes. So yeah, that rho R is the sum of everything that, let's say, that is relativistic depending on the temperature you are standing on or that you are looking at.
Yeah, and then if you take the temperature at which these guys decay at 4 MeV, I'm wondering whether, since these guys are coupled to the plasma, whether they will imply additional entropy injection to the plasma, and so might change neutrino decoupling as well.
Yeah, that's why you cannot go further than this 4 MeV. So there is this work by Steen Hannestad that he looked into what is the lowest reheating temperature in this case. And they got to the conclusion to this 4 MeV. So that's why I'm using that number, that neutrinos are still safe.
Okay, so if the guys decay at that temperature, then you are fine with neutrino decoupling.
Yes.
Regardless of whether these guys are injecting further entropy to the plasma.
Exactly. Yeah.
Okay.
This is
Thank you.
the magic number that doesn't spoil all the Big Bang nucleosynthesis success.
Okay. Thank you.
Yeah. Yeah. So what we expect now for axion production, you will have that the Hubble parameter now has some behavior like this one. That this is the blue dashed line. Here is the standard one for comparison, and this is the axion mass. So the crossing will happen later, let's say to a smaller temperature than in a radiation-dominated universe. So what you expect from this is that the oscillations are delayed with respect to the radiation-dominated scenario. This is one of the impacts of this non-standard expansion. And the other is that the axion energy density gets diluted because, as I mentioned, this entropy injection will go to everything that is present in the thermal bath. And since axions are not, then they will be diluted with respect to the radiation. And you will therefore have to account this by some gamma parameter I put here, which accounts for this entropy dilution between the moment of oscillation and the moment that the field decays completely. So note in here that if everything happens without entropy dilution or entropy injection to the thermal bath, this gamma parameter, would be just 1. And you see that well, actually, no, you don't see it from here, but you can believe me that if you lower the oscillation temperature, this will lead to an increased energy density. So saying differently, if you have a cosmological history that doesn't inject entropy into the thermal bath, but still is not radiation dominated cosmology, and you delay the oscillations, you would expect that the energy density of axions is higher. And this is actually what happens for cosmologies, let's say, produced by these stiff fluids, like with the equation of state higher than 1, that there's no need for entropy injection because the field can just redshift, let's say. But in any case, it will change the Hubble parameter, as I showed before, such that to impact, in any case, the energy density for axions. Okay, so if oscillations happen during this stage 1 or 2 that I showed before, there is only entropy dilution. And the entropy dilution is just the same. It is given by this factor here, this Tn temperature, which is the temperature at which the field ends to inject entropy into the thermal bath, and this equality temperature, in which some power that it depends on the equation of state of this fluid, which for the case of matter takes this really simple expression, and for, let's say, something with the equation of state of -1/3, it would take this expression here. If oscillations happen during the stage 3, meaning where the new field injects entropy into a thermal bath, then the entropy dilution is smaller and is given by this equation here, which again is Tn, but now divided by the oscillation temperature, and with this factor that shows the dependence on the properties of this new field. And again, I put as an example here matter and this other weird fluid here with -1/3. And in this plot here, I just show how it changes for a cosmology with these properties, the oscillation temperature as a function of the axion mass. Yeah, and for low temperature reheating, there is only stage 3. Okay, so now I go to the production of axions during the non-standard cosmology. We studied different cosmologies, we compute analytically and numerically what ranges of masses could give the total or the needed dark matter abundance to account for the dark matter paradigm with axions, depending on the equation of state, and whether the oscillation happened during this adiabatic phase, which is where the field has not decayed yet, and the non-adiabatic phase. So we check cosmologies with equation of state smaller than 1/3. So we took these two as examples, and these show this entropy dilution. But we also look for equation of state higher than 1/3, that they do not have entropy dilution. So this omega equal 1 is it's a cosmology known as kination. And then we also took this omega equal to 5 divided by 3. So these are all results. This is the preferred window I showed you at the beginning for a standard cosmology. And once you require that in a non-standard cosmology, the axion still solves the dark matter problem, you find a new parameter space that opens up. So for instance, if the oscillations happen during the stage 1, this mouse is a bit crazy. If the oscillations happen during the stage 1, you can only account for that in this mass range that is covered by the red, this red region, and with these equality temperatures that are shown in here. So this is a band because we keep the initial amplitude of the field among these natural ranges I told you before. I'm sorry. This 0.5 and 1.8, that is pi divided by the square root of 3. If the oscillation happens during the stage 2, where the field dominates but still doesn't decay, then you find that this is the parameter space where the axion can account for the dark matter. And finally, if the axion oscillates during the stage 3, this is the parameter that you can find. By the way, I didn't mention that we fixed this end temperature, so where the field ends to decay, at 4 MeV, because we know that this is the smallest temperature we could consider for this to happen. And this shows the highest entropy injection. So that's why we fixed to this number. And as you can see, we can reach the smallest axion mass if the oscillation happens during this stage 3. So this means we can open up this window that we had before, assuming that the axion oscillates during a radiation dominated scenario. Well, this opens up quite a bit if you consider that the oscillation happened during a non-standard period. In this case, this is for early matter domination. I have a similar plot for omega equal to -1/3. In here, you can get, or you can reach even smaller masses than in an early matter dominated scenario. And well, the same in here, we divided whether the oscillation happened during which stage of the dominance of the new field. And we also have the same for these cosmologies where there is no entropy injection. like kination, for instance. This is the red curve. But as I told you before, because there is no entropy dilution in this case for the axion field, the preferred parameter space where the axion can be called dark matter is now moved to higher masses because there's no entropy dilution. And we said that if you delay the oscillations, this increases the axion energy density. So this is the case for kination, that you could easily get to masses as high as 10 to the minus 2 electron volt. And for this other scenario with omega equal to 5 divided by 3, then you can even reach the electron volt mass. So these are the conclusions of our work. So in here we showed the coupling to 2 photons versus the axion mass. And this is the window, the preferred window to search for axion dark matter, assuming the standard cosmology, lambda CDM. And this is how you open up this window depending on the cosmology that could have dominated the universe when the oscillations took place. So we show in here that you can get as low as 10 to the minus 10 electron volts in the case of these scenarios with omega equal to minus 1/3. You can open up to here for matter. And on the other hand, if you consider cosmologies with these stiff fluids, like kination and others, you can move to the right of this standard window. So these are the conclusions. And the good thing is that this parameter space is in the range of new experiments that will test the parameter space. So this is opportunities for detection for all these experiments that are planned for the next years, and the same for the high mass region. Okay, I don't know how much, Antonio, till what time?
You still have time, some minutes more, you can continue, Paula.
So how much more, just to know how to speed up?
I think 5 minutes. 5 minutes.
Okay. Well, maybe then I will be really quick to tell you that axions can also be produced thermally in the early universe due to the coupling to gluons and to the coupling to photons. But in the early universe, the coupling to gluons is, of course, much stronger than to the photons, and therefore you can actually guarantee that depending on the axion mass, you will end up with a thermal population of axions. I will speed up. As I said, you can compute the thermal rate, I mean the interaction rate for axions due to this coupling, and find whether these axions thermalize or not. And the conclusion is that I will show you here is that axions with masses higher than this number, 2.8 times 10 to the minus 4 electron volt, always thermalize. So using Planck data, in this paper, they found the constraint that axion mass should be smaller than 0.91 electron volts. And then using Planck plus large-scale structure data, they could even lower this bound to 0.28 electron volts. So we also wondered about what happens to this population once you assume a non-standard cosmology can take place before Big Bang nucleosynthesis. And yeah, and this part I can skip. And basically, the effect of this is that the axions that therefore reach thermal equilibrium will decouple from the thermal bath at a different temperature. And this will lead to different properties for this thermal population. I also have to say, of course, that actually thermalization in a non-standard cosmology is not guaranteed. So even the number I showed you before during non-standard cosmology can change in the sense that that axions do not, depending on the cosmology, might not even thermalize at all. But they still can be hot relics in that case, and have an impact in the early universe. So the impact would be in the contribution to the effective number of neutrinos, in a possible overabundance of hot dark matter, and the impact on large-scale structure formation. So we found the contribution to the number of effective neutrinos. For all this, we did for omega equal 0. So either early matter domination or low temperature reheating. And this is therefore the entropy dilution that affects the quantity for the effective neutrinos, the relic abundance, and the velocity dispersion also of these particles that you can see is the less affected by the entropy dilution. So basically all these factors here are the entropy dilution that are actually the same I showed you before for these non-thermal actions. But this one for the velocity is the smallest one. Therefore, you expect that the impact on large-scale structure could be the less affected by the assumption of a new field that dominates the energy content of the universe. So this is, for instance, how it changes the free streaming length of the axion versus the mass for different cosmologies. So in here, the dashed line is the free streaming for a standard cosmology, and then these two colored lines are for different non-standard cosmologies. And then you can see dramatic changes depending on the properties of these cosmologies. What we did was to use actually the data from this paper. So in this paper, they constrained light but massive relics, and they published their data. They did this for any massive relic independently of the spin. And therefore, we converted this data into data for scalars. And actually, they show their data like this, like the temperature of the relic today versus the mass of the relic. And everything that is in the colored region is allowed, either by 68% confidence level or 95% confidence level. And everything that is white, therefore, is excluded. So using this data that we show here, you can constrain the population for axions. For instance, this so the blue curve is again the data, and now this red line here is the expected axion temperature today as a function of the axion mass. And you would see that everything that touches the blue and from that point on is excluded. But of course, if you change the cosmological history, this line will change, and therefore you will have a different parameter space that is constrained. So to be fair with time, I will only show you my results, which are these ones. This is the axion mass versus the T-end temperature, so the temperature where the field ends to decay. And if you consider a really high temperature for this T-end, you will basically recover standard cosmology, and you will find the bounds for standard cosmology for thermal axions, which from our results, we find a really good agreement with what has been reported in the literature. But once this temperature decreases, you see that the bound starts to relax. And eventually relaxes quite a lot for masses around the electron volt. By the way, all the parameters here that is in gray is where the axion does not thermalize in this cosmology. This one is for low temperature reheating, so omega equals 0. And for comparison, we put here this dotted line, this green dotted line, which is a previous work that only used data from Planck. But the novelty of our work is that we also, besides Planck, we introduced large-scale structure data. And this allows to constrain much more the non-standard cosmology. This is the same plot, but using the coupling to photons. The one before was for the coupling to, using the coupling to gluons. So this parameter space is much less constrained because this coupling is not as efficient as the coupling to gluons. Well, we also look for the possibility that thermal and non-thermal population could coexist together. And of course, for this to happen, we need to consider a stiff cosmology. I mean, a cosmology driven by a stiff fluid. Because as you remember, these cosmologies, the non-thermal population of axions is produced for relatively high masses near to the electron volt. So our results in here, we used also some data for a population produced non-thermally. And basically these are our results. So the lines here show the parameter space where axions can produce a hot population, but it's not in thermal equilibrium. And this number in here tells us about the relic abundance of that population. And the blue band shows the parameter space where the axion can be the cold dark matter. So we found that in a cosmology with omega equal to 5/3, it is possible to have a quite sizable population of hot axions that coexist with a non-thermal population produced by misalignment. Well, this leads me to my conclusions. So the cosmological history before Big Bang nucleosynthesis can shape completely the features of both cold and thermal population of QCD axions. We showed that in principle you can change this hotspot for the dark matter window if you assume that the cosmology is something different than radiation domination when the axion is produced non-thermally in the early universe. And also we studied the production of a hot relic population that in principle, if you assume a non-standard cosmology, is not guaranteed as in lambda CDM. And several cosmological histories can actually escape detection. But on the other hand, the challenge is to look for distinctive features about this population. And this is something we would like to keep studying about distinctive features of the thermal population or hot population that can be can also tell something about the non-standard cosmology, especially in the large-scale structure formation data. And well, eventually detection of either hot or cold relics can help us to learn more about how was the early universe at the moment of their production. And in principle, axions can be fossils of different kinds because depending of the energy or the mass range of the axion, you can find different populations produced by different origins. So axions in that sense are a really active topic because can be produced in very different by very different mechanisms and show different properties that can be searched for in our observations. Well, thank you very much.
Thank you very much, Paola, for the very nice and very complete talk. Question from the audience?
I have some questions. Regarding the first part of your talk, I wanted to ask you about this photon-photon axion coupling that you said that once you have the Pecha-Quinn mechanism going, let's say it's working, if this mechanism is working, you automatically have this coupling to of the axion to the photons. But but in these lines, in the typical plots of the coupling and the mass of the axion, you see like there is no dependence on other parameters. You have only the mass and the high energy scale, but you don't have the like other parameters involved. Or can you go to the first slide, one of the first slides where you put this n E over n plus something in model independent that you said?
Yeah, let me go there.
So, so it wasn't clear to me what, first of all, is E in the last expression and N.
Yeah, so this is the way you construct your model for to let's say account for the Pecha-Quinn mechanism. For instance, I can tell you that so for instance, this KS-VSEED model assumes that you have to introduce new heavy quarks that are colored by the Pecha-Quinn symmetry. And this leads that axions are not coupled to any fermion or quarks.
Yes.
So this is this model, for instance, and this will have a E divided by N number that is distinctive, let's say.
But what is E and N in this?
Well, this depends on the number of these new fermions, of these new quarks that you have to introduce. And E now, I'm sorry that I don't remember. N I know is related to that, but it's totally model dependent.
Okay.
That number. So it could be even 0. But of course, playing with that number, you could also make the coupling to be really suppressed. So this is the the downside of this coupling.
And the fermions running in the loop in one of the slides that you just showed. You have this photon and the triangle. So those these fermion lines correspond to the heavy
Depends on your
fermions.
model, because if you have axions that, so in this DSFZ model,
yes,
axions do couple to
quarks.
To quarks and leptons, yeah.
Standard model quarks.
Exactly. So what you have in the triangle also will depend on your model.
Okay. And my second question is regarding this non-standard cosmology in the beginning, when you introduced this field. Yeah, I was thinking phi as a matter field, but isn't, or what? Because
not necessarily. As I showed you, you can have a different equation of state, and so what will fix omega is the potential that you assume for your
But
field.
normally, in elementary courses of cosmology, when you have W equal to 0, you say that immediately nobody asks about that fact, and this behaves as matter. And normally one uses that as a definition of matter, something that is pressureless. But in this case, you say that it's not.
If you take omega equals 0, this behaves like matter. It does behave.
Yes. Okay. But in this case, in the epoch 2, number 2, W is not. No, it is 0.
It is 0, yes.
But rho, its energy density doesn't go like a typical 1 over T, or no, sorry, exponential of the minus the mass over the temperature, like Boltzmann suppression. You have in this case another kind of dependence on the temperature, right?
I mean, the energy density evolves according to this equation here. So of course, for stage, let's say 1 and 2, you can neglect this term here in the right. And you will just have the evolution, as a matter field. So there's nothing, and also the same will happen in here, where the evolution of the thermal bath will be just the normal one. Only when this parameter is important, the decay rate, then you have a departure, let's say, from that cases.
Okay. Yeah. Okay. Yeah. I'm probably it's my confusion because I am used to work in a radiation-dominated universe, so this changes the things and the dependence on the densities, energy densities on temperature. It's not the same, but yeah, but you have this set of couple equations, so you must to solve those in order to determine
temperature. So if you want to think it like that, in a radiation-dominated cosmology, temperature goes as the inverse of the scale factor, right? So during the stage 3, which the field injects entropy into the thermal bath, this is not the case. And T doesn't go as R to the -1. It's a different power that depends on the
yes,
on the equation of state.
And okay, and my last question is in your work, maybe you said something about it, but what was the relevance of this phi field or there is some phenomenology for this new field that you are introducing in your model, or?
You mean that if we assumed some
does it impact
phenomenology for phi? Because no, we totally remain agnostic about the origin and so on. But of course, there are several motivations in the literature to consider. So that's why we prefer to leave that as independent as possible. But certainly your model will at the end define what is the equation of state and the couplings of this phi and so on. For now we just assume the coupling to the bath, to the thermal bath.
Yeah.
And yeah.
Thank
you. Diego?
Yes, so Paula, so you showed the results for several scenarios defined by different equations of state. So I guess that the amount at which you are able to shift the axion mass or the axion-like particle mass depends on the equation of state upon which you rely. Can one have a qualitative understanding of how much, depending on omega, that mass will shift about the value predicted or expected by standard cosmology?
Yeah, I mean, what we did in the paper was something maybe like the one you are suggesting, in the sense that we wonder, given certain axion mass range, which cosmology can lead to a total production of the dark matter needed to explain dark matter today. And this is at the end what produced this plot here, because in here maybe I didn't mention, we are considering, I went too far, sorry. We are considering really different cosmologies, because in here we just fixed this. So the non-standard cosmology, let's say, has three free parameters: the equation of state and these two temperatures. This we chose to have it this end temperature and this crossing temperature with the energy density of radiation. And for this plot, we fixed the end temperature such that is equal to this BBN temperature, such that not interfere with Big Bang nucleosynthesis at all. And to produce this plot, which we were changing this equality temperature, so the temperature at which the energy density of this new field and radiation get equal, such as to maximize, let's say, the opening or the shift in the axion mass. So if you consider, for instance, a matter-dominated scenario, this is the most you can go to the left. You cannot go any further. I mean, or you could, but you will have let's say, a sub-production of axions, but not the whole dark matter abundance. So in this case, we scanned all possible cosmologies that would have this Tn temperature equal to the BBN temperature, and this equality temperature we left as a free parameter. And this is how we found all this window here.
Okay.
And the same with the other cosmologies like kination and so on.
So can I find an equation of a state for which I can shift the action mass to the, say, MeV level, like 10 to the 6 eV or so, or not?
Well, I mean, in principle, there is a maybe. I mean, let me say it differently. For the misalignment, why the misalignment mechanism doesn't work for heavy actions? Is because you have the Hubble parameter scale as a reference. So you need that the Hubble parameter gets of the order of the axion mass. And if the axion mass is too high, let's say, these oscillations basically cannot happen, and the misalignment mechanism doesn't work. Okay. So that's why it works for low masses. Of course, if you increase the Hubble parameter by introducing new energy, you will increase the Hubble parameter, and maybe you can find that this crossing is possible. But I guess you will need to have a lot of energy, extra energy, in order to do that. And maybe this field could also overclose the universe and so on. So maybe you have issues from that side. So in principle, I would think it's possible, but my fear would be that this would have because you need that the Hubble parameter is of the order of the axion mass for the misalignment mechanism to happen, that at the end it can be a not so viable mechanism.
Okay, thank you, Paula.
Yeah.
More questions from the audience? If there are no more questions, we thank Paola for the very nice and very complete talk. Thank you so much, Paola, for the very nice talk, for the very nice seminar.
For the kind invitation, and thanks everyone.
See you at the next seminar. Thanks a lot, Paola, for the very nice seminar. Bye.
Thank you. Bye-bye.
Bye.
Bye-bye.
Bye.